Shall we start?
Yes, sir. Shall we?
Okay. Yeah. Okay, fine. Good morning, all. You all are welcome to the fourth day of our FDP. So today we have in the first section Dr. P.V. Nidheesh, Senior Scientist, NEERI Nagpur. So he will be presenting on aerated electrocoagulation and its applications towards wastewater treatment. A potential person with more than 100 publications in that particular area. And yeah, now I may welcome Lakshmi to introduce the expert.
Good morning, everyone. Today we have with us Dr. P.V. Nidheesh, who completed his B.Tech in Civil Engineering from Government College of Engineering, Kannur, Kerala, and did his M.Tech in Environmental Engineering and PhD from National Institute of Technology, Trichy. After the completion of his doctoral degree, he worked as an ad hoc faculty at National Institute of Technology, Calicut, and as an associate professor at Vimaljyothi College of Engineering, Kannur. Currently, he is working as a senior scientist at CSIR National Environmental Engineering Research Institute, Nagpur, India. His research interest includes water and wastewater treatment and advanced oxidation processes. He has published around 108 international journal articles, 12 conference articles, 1 book, and 6 book chapters. He is an author of highly cited and highly downloaded articles. He is a reviewer of various journals published by Nature, Wiley, Springer, elsewhere, etc. We are honored to have you here, sir. Over to you. Thank you.
Thank you, Anand Singh and Lakshmi, for a nice introduction. Let me share my slides.
Yeah, you can.
Understood. Is it visible now?
Yes.
Okay. Good morning, all. So, myself, Dr. P.V. Nidheesh, working as a senior scientist in CSIR-NEERI, Nagpur. And the topic is slightly advanced. I can say it is recently a hot topic in the area of electrocoagulation. And I slightly modify the topic also. Now I focusing only on aerated ion electrocoagulation and its applications towards wastewater treatment. So we know that Anand Singh, I am receiving some echoes.
It's okay. It's fine now, I hope. Like when we are unmuting and muting, actually it is giving an echo.
Okay, fine.
Okay, fine.
So you know that electrocoagulation is a old topic. It started in 1961, and of course, so many people are working towards its real field implementation, and there are so many problems associated with the implementation of electrocoagulation process. Let me see what are the issues. And the main advantage of this type of process, electrocoagulation process, you can see that the cost of this process per liter of any wastewater, it may be very less compared to other treatment process. However, now some of the people is already implemented in the real field for drinking water treatment, and some of them are trying to implement for wastewater treatment. So for the participants, if you have any doubts in the from the slides you mentioned, you can note down the slides, and you can ask later. If your query is related to the basic content of the slide, then you can ask at that time itself. So slide number will be at the bottom. You can note it down. So as I mentioned, CSIR-NEERI is an autonomous body under Ministry of Science and Technology. We have CSR labs. We have 38 labs in India working in different fields. And NEERI is one of the organization. It's purely working on environment. And we have several divisions working in different aspects of NEERI, different aspects of environment like air pollution and climate change, environmental materials, virology, health and toxicity. And our division is the environmental impact and sustainability division. We are working on environmental impact assessment and sustainability development, all these things. And we have our headquarters is in Nagpur, and we have zonal labs in Chennai, Delhi, Hyderabad, Kolkata, and Mumbai. And we have other scientific and technical and administrative supporting divisions. This is a brief introduction about CSIR-NEERI, and we have several opportunities in CSIR-NEERI for young aspirants, because now if I see the participants list, most of them are, I think it's in their initial stages of their career. So the people, they want to do the MTech or PhD, they can we have a program called as Academic of Scientific and Innovative Research, ACSR. Through that gate score, you can do MTech, and through interview, you can go for a PhD. In not only in NEERI, any CSR lab you can opt. And other than that, we have a system for project trainee. That means those who are working in other universities, MSc, like MSc, MTech, and BTech students from different universities, they can do their projects in our institute in any CSR labs for a minimum of 6 months. We used to prefer a minimum period of 6 months for doing a project, their thesis work. Then the third option is related to our externally funded projects. So I have mentioned a few positions like typical early stages, like if you are graduate, that means BSc level people, they can join in our projects for a scientific and administrative assistant or a field worker. The age limit is 50 years, and they will get 18,000 plus HRA per month. If you are BSc plus or diploma, then you may get 20,000 plus HRA. Project associate 1, that is MSc or BTech level, they will get 25,000 plus HRA. Then MSc or BTech plus 2 years experience, you will get 28,000 plus HRA. Then there are some other options, that is senior project associate. So that you can you can visit our website and you will get the details. So now I think normally we used to call a open call for a year through that will be it was opened on January and it's closed on May. So again, you may get an open call. So why I asked is, now even we are paying this much of amount, we are not getting a good candidates for doing our or helping for our projects. So coming to our topics, electrochemical methods, I think most of the people knows about the electrochemical treatment. There are so many electrochemical methods. So coming to a typical electrolytic system, this is known as an electrolytic system. There are but commonly known as electrochemical methods. If you are going for a basic electrochemistry, both are different, electrolytic system and the electrochemical system. Electrochemical system is also known as galvanic cell, and electrolytic system is entirely different from electrochemical method, but for the treatment purpose, it is commonly known as electrochemical processes. The difference between electrochemical method, electrochemical cell or galvanic cell with electrolytic cell, that means this cell is difference is that in an electrochemical cell or a galvanic cell, we will generate electricity from that system. That means you may be studied in your 8th standard or plus 2 or in a BSc standard, BScs, or even sometimes in some courses in BTech also, basic electrochemistry. In that, if you are keeping copper and zinc in a copper sulfate solution, then if you are connected with wire, you will get electricity. So that is due to the potential difference, you may get the electricity output from the system. That is known as electrochemical cell, or commonly known as galvanic cell. But in the case of electrolytic system, here we are applying electricity to make some electrolytic reactions in the system. So that means here we are applying a power supply to do some reactions in the electrolyte. So as you know, for an electrolyte cell or any electrochemical cell, there are so many parts. That means we can say it should electrodes. One is anode and cathode. Anode is connected with positive charge and cathode is connected with negative charge of a battery. And this solution is known as electrolyte. It may be a salt solution or any other things, depends on our target, what process, why we want to do it. That means if you are doing for a wastewater treatments, our electrolyte, we can consider this as a wastewater, or for water treatment, it's a water plus the pollutant what we are targeting. So if you are connecting the anode and cathode with power supply, that means DC power supply. Normally we used to prefer it as a DC because the DC will get a constant supply without changing the polarity. But in the case of AC, you will get supply with fluctuation, that the polarity used to change. So that will create a lot of issues in the system. Even so, that's why we used to prefer as a DC supply. So if you are connecting an anode with a DC power supply, that means positive power if you are giving. So there are 5 reactions occurs in an electrolytic system. That means first one is a electrooxidation. That means always oxidation of any ions will occurs at the anode surface. Anode is known as surface is applicable, only oxidation will occur. For example, if chloride is in the system, chloride. So chloride is, it will if it is there, it will attract towards that system anode, then it will convert into chlorine gas or hypochlorite or hypochlorous acid. That is depends on the pH. So that is the oxidation process. So if anode oxidation occurs, means then definitely cathode reduction will take place. For example, ferric ions are there, it will convert into ferrous ions. That is known as electron reduction. Then electrode dissolution will take place in some kind of electrodes, like we used to call it as unstable electrodes, like metal electrodes. For example, iron, aluminum, manganese, zinc. So all these metals, if you are using it as a anode, then what will happen is, say this M is a metal. So depends on their valency, it will dissolve. That is also depends on several factors that we'll discuss later. That is known as electrode dissolution. So at the same time, this will migrate, so that there is a fifth reaction, that is migration of cations and anions. That means if it is produced here, it is a positive charge. As I mentioned earlier, cathode is a negative charge. So it will migrate towards the cathode and it will deposit over the cathode surface. That is known as electrode deposition. And that is the fourth reaction. Fifth reaction, I already said, migration of cations and migration of anions. If anions are there, that means chloride is there, then it will migrate towards anode and it will oxidize. If positive cations are there, means it will migrate towards cathode surface and it will deposit over the surface. So depends on the process. We can divide all the electrochemical process into two different categories. That is, one is a separation process, another one is a degradation process. So separation process, as I mentioned, it is only a process. It will separate the pollutant in aqueous phase to another phase. Most probably it is in the solid phase. For example, electrocoagulation, electrosorption, electrodialysis are the examples of this separation process. For example, this electrosorption, if you are considering the electrosorption, you may know that adsorption of adsorptions process. That means if an adsorbent is present in the, say, activated carbon is in the water and any pollutant is there, then depends on the charge, the pollutant will adsorb over the surface of activated carbon. So same principle is used in electrosorption process, where we are using an carbon electrodes as a cathode or anode. Then if you are supplying electricity, then this pollutant depends on the charge, it will adsorb out to the surface of cathode or anode. So that is known as electrosorption. Mainly on cathode, because the deposition will take place at the cathode. Then another process we can known as the degradation process. That means even we can divide into the degradation process. Degradation process, normally we are focusing on the degradation of organic pollutants like phenol or dyes, all these process, all the compounds. It's very difficult to remove from, or toxic compounds, remove from the water. If you are using a separation method or even arrow or reverse osmosis, all this process, they can separate these pollutants from the water. But the toxic content always there in the system, because it will be as in the sludge or anything, it will be there as a toxic compound. So that's why we are focusing the process like commonly known as a degradation process, where we are generating some kind of oxidants in the system, electrochemical system, for degrading all these compounds. Again, we can divide into this process into two. One is oxidation process, second one is advanced oxidation process, commonly known as electrochemical advanced oxidation process. Oxidation process, what I mentioned here is it is also known as indirect electrochemical oxidation. Here what we are using is, if you are adding chloride in the electrochemical electrolytic system, so this chloride ions will attract towards the anode surface and it will generate chlorine gas. So you know that this chlorine gas or active chlorine, generally we used to call it as a active chlorine species, like chlorine gas or hypochlorous acid or hypochlorite. It is having a high oxidation potential around 1.5 electron volt at standard conditions. So these pollutant, it will attack the these active oxidants will attack the pollutants present in the water, and it will degrade. So that is known as indirect electrochemical oxidation. It is a very old process. And coming to the electrochemical advanced process, and this is a hot topic in this area, because most of the process are started in the early period of 2000 in this range. Electrofundation started by Professor Oturan from France and Enric Billars from Spain. Two groups, they simultaneously started working on this process, and it is first paper is published in 2000 by Oturan. That is 2,4-D degradation by electrofundation process. So that is the first paper I can say, and another paper is later, same group only published the same similar paper. And peroxycoagulation is a modified version of electrofundation, and anodic oxidation, it is another version of advanced oxidation process, electrochemical advanced oxidation process. I will explain the basic principles of this process later. Then coming to any electrolytic system, the Faraday's law of electrolysis is applicable, but if that is applicable only if the anode is, what we are using is a metal anode. That means we used to call it as a sacrificial anode, or it's a unstable anodes, like iron, aluminum, all these things. So Faraday's, the two laws are there. We used to call it as a Faraday's first law and second law. This is the law is stating that the amount of in molar amount of ions coming from the anode is directly proportional to the electricity transfer, that means the power supply, and it is also directly proportional to the equivalent weight of the metal ions that is dissolving. So finally, we can conclude that equation as M. That means molar quantity of that is mass of elemental material coming out from the anode is equal to Q is the charge we are applied divided by F, that is a Faraday's constant, into M by Z. M by Z is equal to is known as equivalent weight. M is the molar weight and Z is the valency. Actually, equivalent weight is the general equation for a equivalent weight is equal to M by Cc. Cc is a combined capacity. That means instead of Z, it will be Cc. So Cc is equal to the number of protons for acids. It's a general equation, not applicable for electrochemical system. M by Cc. Cc is equal to is known as combining capacity. For combining capacity for acids, it's equal to the number of protons. For example, hydrochloric acid, number of proton H plus is equal to 1. Sulfuric acid H2SO4, so 2 protons. So Cc is equal to 2, like that. If we, in the case of alkali, it is equal to the number of hydroxyl ions. For example, sodium hydroxide NaOH. OH is equal to, that is number of OH minus ions is equal to 1. So that is the Cc. But in the case of a salt or anything, Cc is equal to the valency. For example, NaCl. Sodium is a positive charge and chloride is a negative charge. Both are 1. So the valency is equal to 1. So that's why this equation is written like this. That is molar mass, molecular weight divided by Z. For example, if aluminum, we are using aluminum anode, then Al3 plus will come. So molecular weight of aluminum, I think it is 23, if I am not wrong, divided by Z is equal to 3. So that is a valency. So this is the Faraday's law for electrolysis, and this law is applicable only for if we are using this anode as a sacrificial anode, or we used to call it as a sacrificial anode or unstable anodes. Okay, then coming to the electrocoagulation process. So we know that coagulation you used to apply for a water treatment process. That means if you are adding a coagulant in the water, it will destabilize the pollutant, especially the clay particles, and finally it will become a bigger particle and it will settle down. That is the coagulation process. So same principle we are applying in the electrocoagulation process for removing the pollutants. So this is the typical example of electrocoagulation process system. That means if you are using a metal anode, metal as an anode like aluminum, iron, all these things. So the Mn plus particle used to come. That means if it is aluminum, Al3 plus will come. So there the reactions will coagulation takes place, so that it will be precipitated as a sludge. And there are other 2 reactions occurs in any electrolytic system. One is a oxygen evolution reaction at the anode, and the cathodic reaction, that means hydrogen evolution at the cathode. See, the oxygen evolution reaction also is depends on the potential of electrode what we are using. Normally these reactions, if you are using aluminum or iron, it will not take place much in the electrocoagulation system. But other electrodes, if you are using, then these reactions will take place. But this reaction, that means cathodic reaction, always takes place at the cathode surface. That if you are using metal anodes, metal cathodes like iron or any metals. So this hydrogen is generated at the system. So this will float. So what will happen is this pollutant, and it is reacted with the I can say the flock. So the hydrogen will trap on this precipitate, so that will float over the surface. So 2 types of sludge we used to get from the system. That means it is at the top and at the bottom. Normally this reaction, that means the floating at Yes. Hello?
No, it's fine. Actually, it is 1 minute.
Okay.
Okay, sure. No, it's not question actually. It's they have unmuted. You can continue.
Okay. So this reaction, that means hydrogen evolution reaction and float formation on the surface, is also known as electroflotation. Normally, nobody will use this process for the exclusively for treating the water because the efficiency may be very less, and trapping the pollutant in the hydrogen gas, everything is a difficult. So, but it is a part of electrocoagulation process. So this is, if you are running an electrocoagulation system, you will get these type of reactions. That means if you can see as a turbid solution, and if you are running the treating, then you will get a clear solution after maybe 30 or within 1 hour, you will get a good results for this electrocoagulation system. So this is one of the study done in Aerated by Ashwadi. It's a bilge wastewater. Bilge wastewater is nothing but the wastewater generating in the ship cleaning facilities and all. So it contains oil, all these things, organic compounds, all these things. So after running, you can see that two types of sludge, top sludge and bottom sludge. Then we find the volatile fraction and fixed fraction. Volatile fraction is nothing but organic compound, and fixed fraction is nothing but the inorganic fraction. That is why normal our procedure, that means muffled furnace, what we are keeping in 600 degrees Celsius for 20 minutes. And a normal oven, we used to keep 100 degrees. Normal procedure, we find out the organic and inorganic fraction. You can see that in the top portion, it is containing 93% as in organic content, very less content of inorganic fraction. But in here, you can see it's containing higher amount of inorganic content compared to the top sludge. So what it's meaning that in the case of electroflotation, the lightweight organic compounds, I can say it's oil or aliphatic compounds, small compounds. So that will trap along with this hydrogen generation, and it will float over the surface along with some amount of precipitate, that means generated from the metals. That means if you are using aluminum hydroxide, some amount. That's why the fraction is very less. But here at the bottom, you can see that most of the sludge, that means contains inorganic content. It means that means the precipitate coming out from the anode is react with the pollutant, and it will settle at the bottom. That's why we are getting higher amount of inorganic content at the bottom. So this is another treatment we had done in when we were in Trichy. That article it's published in ASC, that you can refer it. So that is for a landfill leachate. We know that landfill leachate, and it's also for a stabilized landfill leachate. Stabilized landfill leachate treatment is quite difficult because its BOD by COD ratio is very low. So biodegradable fraction is very less. So we need to go for any other treatment, physicochemical treatment for treating this stabilized landfill leachate. So we tried with this treatment using electrocoagulation. So this is the result, and even we added fly ash as a electrolyte. So that means to improve the efficiency. Even this last leachate is having high TDS, so that reaction used to take place. But to improve the efficiency, we added fly ash for enhancing some kind of efficiency. And we targeted heavy metal removal from leachate. So ultimately, it is a combined action of electrocoagulation and I can say it's adsorption. But electrocoagulation itself, it gave good results compared to Even we tried with, here we used aluminum as an anode. So we tried with chemical coagulation, that means CC. Then we compared the efficiency. CC also we depends on weight of aluminum. That means from the Faraday's law, we find out the aluminum coming out from the system, and also we check the weight loss before and after the treatment from the anode. So based on that one, we calculate how much alum is required. Then we compared with, then we you've done the treatment, chemical coagulation at different conditions. Then we see that we can see that the efficiency of electrocoagulation is significantly higher compared with chemical coagulation. So that is the advantage of electrocoagulation system compared to chemical coagulation system. For example, most of the times we cannot remove all the components from water, all the pollutants from water using chemical coagulation. But in the case of electrocoagulation, most of the pollutants can be removed. For example, if you are adding alum, you are adding alum will generate aluminum hydroxide, and this flux will generate pollutant will generate. But at the same time, you are adding sulfate in the system, in the water. So that is also an issue if you are adding higher amount of alum in the water. But if you are treating this water with even its sulfate also can be removed from water using electrocoagulation. So this is the overall view of an electrocoagulation process and their efficiency. We can say that from water, the electrocoagulation process is effective for removing turbidity, hardness, phosphate and nitrate, fluoride, arsenic, copper, mercury, lead, cobalt, chromium, nickel, boron, cadmium, strontium, cesium, iron, oil, etc. from the water. So many literatures you will get for the water treatment using electrocoagulation. So many target pollutants, even very minute, we can say ppb level compounds also, it can be removed effectively from the water using electrocoagulation process. And this process is also effective for the removal of treatment of wastewater, like textile wastewater, oil wastewater, metal cutting wastewater, landfill leachate, bilge wastewater, tannery wastewater, pulp and paper industry effluent, potato chips manufacturing wastewater, poultry slaughterhouse wastewater, egg processing wastewater, dairy wastewater, paint manufacturing wastewater. So many wastewater treatment papers or treatment method using electrocoagulation is available in the net. Then if you are checking the publications list, is that's this data I took it from Web of Science. The publications, you can see that in the initial period it is very less publications, but in after 2005 you can see the publications are increasing. That means the researchers are attracted towards this electrocoagulation process. And coming to the countries, USA is having higher publications in this area than Turkey, China, India is in the 4th positions. Then this is another important thing when we are considering about the electrocoagulation process. So normally heavy metals, I mentioned that heavy metals can be removed from the water by electrocoagulation process. So normally we will use a lime treatment for heavy metal removal, right? So what we are happening is if you are adding lime in the water, so if depends on the pH, if the pH is neutral, obviously the lime addition, because it is a hydroxide ions are there, so it will shoot up the pH in alkaline conditions. But if the initial pH of the water is in the neutral pH or slightly acidic, it contains higher amount of carbonate and bicarbonate. So with the lime addition, lime will be converted as a calcium carbonate. So the calcium carbonate is a precipitate. So that is the main mechanism how it is removing the one kind of removal of this pollutant or heavy metals from the water by lime addition. But the increase in the pH was also have influence on the precipitation of these pollutants. For example, silver will precipitate after pH 9, and the lead will precipitate after pH 8, and copper again it's after 6, and depends on the pH it will vary. So for example, at pH 12, the minimum, if the concentration of lead in the water is say around 0.07 milligram per liter, it will precipitate. Okay, if silver is present in the water at pH 12 in the range of 0.01 milligram per liter, so it will precipitate. That means it will precipitate as silver hydroxide. But in the case of lead, you can see that lead is that it's a carcinogenic. It's a very heavy metal is a very carcinogenic in nature. So this lead content it will precipitate only if the concentration is above 10 milligram per liter. So that type of pollutant targeting with lime treatment also is quite difficult, because see, lead concentration above 10 is difficult, because that means below 10 it will be present in its dissolved form. It will not precipitate. But in the case of electrocoagulation, these pollutant, even in the ppb level also we can remove it if you are treating with any electrochemical treatment. Even electrosorption also is effective for removing this pollutant even in very less concentrations. Copper is fair good compared to other pollutant, even very less concentration like 0.001 at pH 8. It can be removed by some slight changes in the pH. And you know that in Morse method is normally it is just a discussion, or I put a question, that means why pH is very important in Morse method. We are using a silver nitrate and titrate against potassium chromate indicator for finding the chloride. That is the Morse method what we are adopting for chloride analysis in the volumetric analysis. So here pH is very important, and if you are referring APHA or any other IS standards for chloride analysis, you can see that the pH of 7 to or 6 to 7, that means near to neutral pH is the optimal pH for Morse method. Otherwise, you will get error in the analysis. If the pH is higher, then what will happen? This silver will be precipitated as a silver hydroxide. So you will not get any endpoints. So before going for a analysis, you should check the pH for chloride analysis. If the pH is below 6 or in slightly acidic below 5, then what will happen is in dichromate, it is in a CS3 plus, then it will convert into CS6 plus. So that changes will be also there. So we will not get any endpoint. So that's why pH is a very important parameter for Morse method. So since I put this diagram, that's why I just given a question for discussion. So coming to the mechanisms of electrocoagulations, you know that there are 4 mechanisms for coagulation, chemical coagulations. One is double layer compression. Second one is interparticle diffusion, interparticle bridging. Sorry, not diffusion, interparticle bridging. Third is enmeshment in precipitated, also known as sea-flow coagulation. Fourth one is adsorption and charge neutralization. But the first two, that means double layer compression and interparticle bridging, is normally not occurs in an electrocoagulation system. In double layer compression is nothing but if you are considering a clay, normally we used to take clay as a model pollutant, because in normally coagulation we used to apply for the removing turbidity from the water. So clay is always, it's negatively charged in the normal conditions. That means if pH above 4, most of the clay particles like Calicut or bentonite, all these particles having the point of zero, that means the surface point of surface charge or is 0 at pH around 4. So above that, it will be always in negatively charged. So normally our water pH will be 7 or 8 in that range. So it is highly negative. So it will be always in repulsion, all the particles. So that will be in suspended form. That is known as stable form of clay particles. So we need to destabilize it. So for that one, if you are adding any salt in the system, for example, sodium chloride, if you are adding, or any sodium sulfate, anything, sodium will attract towards this clay surface because it's a highly negative charge. Sodium is positively charged. So it will attract. So it depends on the sodium content. The effective charge in that area in the surface will be reduced. So double layer is nothing but, you may know that Helmholtz layer. It is a single thin layer over this positive, or depends on opposite charge or charge layer over the surface of the material. And the stern layer, it is highly loose layer compared to Helmholtz layer. So the thickness of double layer is the combination of Helmholtz layer and stern layer. Normally for a clay particle at the normal pH, it will be around 30 nanometer. So if you're adding this, the concept is, if you're adding the sodium or sodium chloride or sodium sulfate, the sodium will attract towards this surface and this layer thickness will reduce. So that means depends on the concentration of sodium, it will, that repulsive force will reduce. Ultimately, it will settle down. The practical example of this double layer compression you can see in estuarine zone. That means river sediments. That means what are the sediments is carried out by the river. It will in the sediment, that means estuarine zone, it will settle down. That is commonly known as delta formation. How it is happening? That means in estuarine zone, you can see that from this sea, estuarine zone is the part where we can say the river is meeting the sea. So in that part, what is happening, because of wave action, this chloride is coming towards this estuarine zone, and normally this estuarine zone, the chloride content is very high. Chloride, that means sodium chloride content is very high. So this clay is coming out along with the river. That means, especially in this rainy season. So most of the these particles having high, that means because of the negative charge, it will be always suspended. It will not settle down. So once it's coming near to the estuarine zone, because of this sodium content, higher sodium content, so the double layer compression will take place, and all the clay particle will settle at this estuarine zone. That's why delta formation normally occurs at the estuarine zone. Then coming to the second mechanism, that is known as intraparticle bridging. Normally, we know that normally we will use polyelectrolyte for the as a coagulant. PDDMA, so many polyelectrolytes are. So this polyelectrolyte is having some charge at the both ends. So see, if we are using a clay particle that is a negative charge, so we should use a positive charge polyelectrolyte. If you are adding, then it will attract all the at the both ends. Then it will form a big flock. It will settle down. That is the intraparticle bridging mechanism. So these both mechanisms, that means electrocoagulation, in electrocoagulation, both mechanism, double layer compression and intraparticle bridging, is insignificant. So the third and fourth are significant. That means enmeshment in precipitate, or it is also known as sea-flow coagulation, adsorption, and charge neutralization. So coming to the enmeshment in the precipitate, you know that if you are adding alum, it will precipitate as aluminum hydroxide. Then if you are adding a alum in the water, or any aluminum salt in the water, it will precipitate aluminum hydroxide in the pH, say around 6 to 7 or 6 to 8. That is the optimal pH for aluminum hydroxide precipitation, as in the case of this silver and all. No, this is we used to call it as a solubility diagram. So if you are adding aluminum, the diagram will be like this. At the pH 6 to 7, it will precipitate. So this is a gelatinic in nature, that means sticky in nature. So if it is colloid with the pollutant, it will stick over the surface and it will become a bigger particle and it will settle down. So that is known as a enmeshment precipitate mechanism, or it is also sea flow coil. That means it's just like a sweeping the dust particles in our house. That's why it is known as sea flow coagulation. So there is an relation for optimum coagulant dosage versus turbidity. That is, it is having an indirect relationship between the optimum coagulant dosage and turbidity for this type of mechanism, sea flow coagulation mechanism. So this is one experiment what we had done in when I was in NIT Calicut. We used that hibiscus leaf extract as a natural coagulant for removing turbidity from the water. You can see that there is for a high turbid solution, the optimal coagulant dosage is around 6 milligram per liter, but in the low turbid, it's around 50 milligram per liter solution. Low turbid solution, the pH, dosage of, this is for alum. Even the same result we got it for hibiscus also. The optimal coagulant dosage is 10 milligram per liter. That means there is an inverse relationship. What will happen is, in the case of high turbid solution, small amount of flock is enough because higher amount of particles are there in the system. So the collision will be high. Okay, but in the case of so that all the particles will stick on this some small amount of sludge. But in the case of low turbid, that means number of particles in the water is very less. So we need a lot of aluminum hydroxides to remove all these pollutants. This data is available in the is already published in Soil, Air and Water Pollution journal. So coming to the adsorption and charge neutralization mechanisms, here depends on the pH, the speciation of the coagulant occurs. That means not only coagulant, any metals it's occurs. That means if you are using iron, all the iron, that means ferric compounds, all the ferric ions will be in their Fe3 plus form at pH say around less than 3. If it is pH around 4, it will be in the FeOH2 plus, or at pH 6 it will be FeOH2 plus, or in FeOH3, that means in 8 pH FeOH3, and FeOH4 minus at the pH above 10. So depends on the pH, the species will be like this. But in the case of ferric, normally if you are aerating or water is there, means ultimately these other precipitate FeOH2 plus or FeOH2 plus or FeOH4 minus, it may be some amount will be precipitated as FeOH3. This is a normal flow what we are getting in the neutral pH, but these are all species, these are all the also as a precipitation. It will all the comes as a precipitation. So coming to the adsorption and charge neutralization mechanism. See, if suppose your target pollutant is like humic acid, that is a normally negative charge, or is a clay particles, negative charge, and in the pH say around 6, FeOH2 plus, that is a positive charge. You can see, so it will attract. So it will become a bigger particle and it will settle down. So that is known as an adsorption and charge neutralization mechanism. So as I mentioned, some of the treatment units also already implemented in the real field. One is for arsenic, it is for fluoride removal, what we developed in NEERI. This is a solar-based system. That means for DC power supply, it is power supply is from the solar panel. And this is other two is developed in CSIR-NEERI. That one is for arsenic removal and another one is for nitrate removal. That is community level. That means for 100 people, like that. even there are some other electrochemical units. That is, one is from arsenic removal unit developed by what is his name? University of Berkeley. They already implemented in Bangladesh and some parts of India. So there are small community level units already developed by different researchers in the world. So coming to the aerated ion electrocoagulation, till now we discussed about the electrocoagulation and its applications. Now we will slightly move on to our topic, that is aerated ion electrocoagulation. So aerated ion electrocoagulation, why we need for aeration? That is the question. So this is the base paper from which I started working on this aerated ion electrocoagulation. This is the same group, that means that University of Berkeley group, they were working for arsenic removal. They implemented the system in the West Bengal region and all. They find what is the problem in the if you are running in the real system. They found that this magnetite formation is very high, and what is happening is initial stages this electrode dissolution is very high, but in later stages it is very less. You can see the magnetite formation over the surface of this electrode. So this normally we used to call it as a passivation of electrode, and we can reduce it by mechanical cleaning, or if you are changing the polarity, all these things, we can reduce these passivations. But in real field implementation, sometimes it's quite difficult to do all these things. And even the studies is found that the this rate of reaction, this magnetite formation is very high because of the very less oxygen in the content. So that's why we started working on this aerated ion electrocoagulation, and fortunately we got some good results in comparison with electrocoagulation, basic electrocoagulation process. So now we are targeting this removal of this arsenic from the water by aerated ion electrocoagulation. You know that arsenic is a carcinogenic metalloid. It's a metalloid, not a metal, not a gas. It is a metalloid, and you know that in most of the parts of the world is affected by the arsenic contamination, and this contamination is mainly from the natural minerals, not mainly by the industrial activities. And among all the countries, we can say that the Ganga or Brahmaputra plate is highly affected by arsenic contamination, especially the West Bengal region, Chhattisgarh, and Bangladesh. All this region is highly affected by these arsenic contaminations from the even in the water. You can see for example in the West Bengal region, you can see the rate of the amount of arsenic in the range of 500 milligram per liter, or 500 ppb level, not in milligram, ppb, microgram per liter, or near to 1 milligram per liter in some that is severely polluted areas. So if arsenic is in water, it will finally it will comes to a cancer stage. So it is the cancer stage. It occurs normally in different stages. It's known as a preclinical stage, and second one is a clinical stage. Third one is a complications and malignancies. That is a cancer stage. So initially it will detect from the urine, body, tissue, etc. from our body. But normally at that time you will not see any symptoms on your skin or any parts of our body. But if you are using drinking the contaminated, that means arsenic contaminated water for at least for 5 years, then some small dots will comes in our skins. That is known as clinical stage. Then the internal organ will be affected. That is known as a complication stage. Finally, it will come as a cancer, end with a cancer stage. That is known as malignancy stage. Then, if you are, this is the NRC data what they have published report. If you are using a 1 liter water containing 50 ppb, 50 microgram per liter of arsenic, it may lead cancer stage. That means the ratio is 13 in 1,000 people. That means it may happen. That is the probability. Then, if you are considering the standard permissible limits, you can see that some countries they kept drinking water limit less than permissible limit less than 10 microgram per liter, that is 10 ppb, less than 10 ppb, like Australia 7 ppb, Denmark 5 ppb, US especially New Jersey it is 5 ppb. Then it is equal to 10 ppb in Canada, European Union, EU, that means Germany, Japan, Namibia, Nigeria, Taiwan, and US, other parts of US, and WHO also. They kept us 10 ppb as a permissible limit. Mexico, so 35 limit. And the people, countries like India, Bangladesh, Argentina, Bahrain, Brazil, Chile, all this country, they kept it as permissible limit as 50 ppb, but our desirable limit is 10 ppb. And the thing is, see, even this area is highly affected, but our permissible limit is 50 ppb. Other area like this Australia and all, it is not affected much, but their permissible limit is very much lesser than our limit. Even in Bangladesh and India, we kept it so 50 ppb. That is very high compared to other countries, and we are severely affected, especially this northeast part. Then our target is not on the arsenite, that means 5+ removal. It's our target is on arsenite 3+ removal. That means normally arsenic will be there in organic and inorganic forms, but normally in the water it will be in inorganic form, and inorganic form also in two species ionic forms. One is arsenic 5+, AS5+, that is known as arsenate. Then AS3+ is known as arsenite, NITE. And if you are going for a speciation of this arsenite, you can see that it is all having some charges. You can see it is always negative charge in the water, in all the pH conditions, so that we can remove this arsenate easily by any adsorption process or any other process very easily. But if we are coming to the arsenite, only the at pH above say 8.3 or 8.5, it is having the positive charge. But most of the cases below pH 8.5, it will be in non-ionic form. So the removal of this arsenite is quite difficult compared to arsenite removal. Otherwise, we need to treat the water above pH 10 so that the adsorption can take place. That is another way. So coming to, so our removal is arsenate removal. So we can remove this arsenate by oxidizing this arsenate to arsenite, that means 3+ to 5+ by using some oxidants. Further, we can remove by any suppression methods like any adsorption or any other thing. Then we tried the removal of this arsenite 3+ by aerated electrocoagulation and without aeration. That means conventional electrocoagulation. We can see that conventional electrocoagulation at every pH, the removal is very less, and we used 1 milligram per liter as a target arsenic concentration, 3+ concentration. And if you are aerating, the efficiency is very high in all the pH conditions, 3 to 11. Then we checked what is happening with the aeration. Then we find a speciation of this arsenic 3+ and 5+. Then we can see that this is the arsenic 3+ concentration is decreasing, and even this is a total arsenic concentration. It is the degrees, but there is some difference. You can see that That means some arsenic 3 plus is oxidizing. This is the arsenic 5 plus concentration. That means it is increasing. That means here this arsenic 3 plus is oxidizing to 5 plus, then removing by conventional electrocoagulation process. So that is the thing happened in aerated electrocoagulation process. But in the case of normal electrocoagulation, this oxidation will not take place. But if you are adding aeration, it will oxidation will take place. But this aeration and this oxidation is not by the oxygen, because oxygen is dissolved oxygen is not capable of oxidizing arsenic 3 plus to 5 plus. Then we checked what is, these results are already published in Separation Science and Technology. It's available in online. Then we checked what is the possibilities. Yeah, then in 2012, similar, that means the what I meant, University of Berkeley group, that means Gadgil group. They already published one paper. They mentioned that if you are aerating, the Fe0 will comes as Fe2 plus, and the oxygen will convert Fe4 plus. They produced a mechanism in stating that this oxygen will convert as a hydrogen peroxide, H2O2, and this hydrogen peroxide will convert, hydrogen peroxide is an oxidant, so that will convert Fe2 plus to Fe4 plus. But this reaction will not take place in the water, because hydrogen peroxide will not generate in any electrolytic system by only the oxygen addition to an Fe system. But they also mentioned the ferrite formation. That's why this oxidation takes place. Then we found another article, that is, it's a normal chemical coagulation. That means they use ferrous chloride or for the removal of arsenite 3 plus, and they aerated it. So because of this aeration, this Fe2 plus will convert into Fe3 plus. Then finally it is converted into Fe4 plus ferryle ions. These ferryle ions is converting AS3 plus to AS5 plus. So that's why this oxidation is stationary. So we also propose the same pathway. That means this that means superoxides, then hydrogen peroxide is forming, then it is converting into Fe4 plus. That means from the electrode, the Fe2 plus is converting, then that will convert it as this FeOH plus, that means flock. Then because of this H2O2 production, that means that will convert it into, that will it will oxidize to Fe4 plus. Fe4 plus is having a good oxidation capacity around 1.8 electron volt, in that range. So that can oxidize this arsenic 3 plus to 5 plus, but oxygen cannot oxidize this arsenic 3 plus to 5 plus, because the oxidation capacity, oxidation potential of oxygen is very less. So thing is, we propose the oxidation is by ferryle ions. So for, and then we need to find the formation of ferryle ions in the water. So one method is electron spinning spectra, but that is we don't have this facility. So another method is we need to go for a scavenging reactions. Unfortunately, this scavenging rate of these ferryle ions with the arsenic 3 plus is very high compared to other scavengers. This is in the range of 10⁶ liters per moles per second. So we need to find another scavengers. So chloride is very less rate of reaction with ferryle ions. Nitrate was very less. So we, it's okay, fine, but this determination is difficult. So we tried for other methods, like DMSO is a one method. That means if you are if ferryle ions is present in the water, DMSO will react with that one. So by HPLC we can find out the peak. That means normally in DMSO it will give a peak at around 24 something. So there will be a shift in the peak around 21 something. So that shift we can identify, that shift, that means another compound. That is the another method of finding the ferryle ion formation. even we tried that, we couldn't succeed it because of some issues. Again, we are trying that. Now instead of that one, we tried with ethanol. Ethanol is having good reaction rate with the ferrol ions. It's around 2.5 into 10 raised to 3 liters per moles per second. So we did 3 types of experiment. That means electrocoagulation with ethanol, black colored, and electrocoagulation with ethanol in aerated. That means aerated electrocoagulation of ethanol, and only with aeration. So what is the effect we are? And we check the COD removal from the system. We can see that in air, only the aeration, there is no change in the reduction in the COD. That means air is not, cannot degrade any ethanol from the water. Then only the electrocoagulation of ethanol, we can see some reduction is there. That means it can generate the flock. But in the case of aerated electrocoagulation in ethanol, you can see that there is a sharp decrease in the COD reduction. That means ethanol is in electrocoagulation, it can be removed, separated this much amount, say around 6,000 to 5,000 COD. That means around 1,000 COD can be removed by electrocoagulation, but it can remove around, say, 6,500 to around 3,500. That means around 3,000. That means around 2,000 additional removal is due to ferrol ions. That means oxidation. So that's why this is the one experiment we carried out to prove that ferrol ions is generating in the system. Then depends on the air also. This, what I said, the sludge what we are getting is changing. That means this is the same group. That means University of Berkeley group, Gadgil group. They studied the aerated and without aeration, what is happening in the system. Here you can see that Fe2 plus is coming from the, if the DO is present, it will convert it all the iron. That means it will convert it into lepidocrosite or goethite. Goethite and lepidocrosite are, we can say it's only that change in the alpha and gamma with the same composition. But in the case of DO, if absent, then it will convert it as a green rust, or finally it may convert it as a mannetite if only DO is absent. But if you are aerating, even if it is green rust is also generated, if DO is present, it may convert into lepidocrosite. So in the initial slides, I saw that I shown that this mannetite formation over the surface. I think this is the main reaction, because DO, that means dissolved oxygen, will be very less in the system. So for treating the arsenic, normally we will use our target water is our groundwater. Groundwater, definitely the DO will be very less. So that's why we are getting very less efficiency and high passivation rate and mannetite formation. So DO is very important for an ion electrocoagulation. Even this is our result. That means we analyze the sludge. We found a lepidocrosite, but contains several other compounds also. It's a mixture of so many iron oxides, and it's some link between iron oxide and arsenate formations in the sludge, and it is a pure amorphous solution, amorphous sludge. You can see that amorphous nature of this sludge. Then we tried this aerated electrocoagulation in continuous flow process. That means initially we carried out in batch method. Now we carried out in continuous study. Same ion electrocoagulation in 2 rows. Initially we carried out the experiments with 5 liters. Then this one we carried out with 10 liters in the continuous flow method. That means one baffle is there. This is the inlet. It is coming and outlet is coming here. Inlet and outlet, and it is peristaltic pump is used to for inlet and inlet for. Then two different flow rate, 5 liters per hour and 10 liters per hour. So actually we target 50 liters volume, working volume, and then we got a comment from the reviewer for one of our paper that even for 5 liter, why you want to go for a 5 liter because this is a carcinogenic and it contains a lot of, you are generating that much of sludge. Anyway, we are disposing all the treated water and sludge in our authorized distilleries that we used to discharge in the TSDF. Then that's why we reduce the volume from the 50 liters to 5 liters to study the flow rate after in continuous flow experiments. Then 5 liters per hour and 10 liters per hour we tried. That means every day we run for 6 hours. This is day 1. 6 hours we run. Then we will stop it. Next day again we will start. Again third day we will start. Like that we continue the experiments. So what is our idea is, so suppose if we are implementing this system to a household or a community, in daytime, say 6 hours, we will run the reactor, and next day, so that much amount, 6 hours means 6 into 5, 30 liters we will get. Or if you are increasing the volumes, you will get the required amount. So that's 6 hours running time we kept. Then again, what will happen is you can see that this after 5th day, we are getting, that means efficiency is decreasing, 5th and 6th day. And this, if you are, so that means the passivation started occur at the surface of the anodes after 4th day of experiment. That means the surface will be manated or some iron oxides formation over the surface. So one method to remove this passivation is we need to clean it mechanically. Another method we tried is changing polarity. That means after first day, next day morning we change the polarity. That means both are iron electrodes. So if the first day iron anode will be second day's iron cathode. So like that we changed it. Then we found that there is some that the passivation is controlling by this method. Then coming to the increase in the flow rate, you can see that if you are increasing the flow rate, even after third day, the passivation is high and there is a lot of that means that system cannot handle that much of thing. So the change in polarity is effective in this case also, but even after 5th and 6th day, we are getting some amount of arsenic from the outlet. Then, as I mentioned, the sludge containing arsenic and its disposal is also an issue. So what we proposed, what we had done is we used to call it as a stabilization of sludge, solidification of sludge. In concrete, we added, that means some percentages. We use M20 mixtures, then M1, that in different concentration of arsenic were added. That means 0% is a mixed 1, mixed 2 is a 1.5% of arsenic sludge, and we find the compressive strength. These experiments were carried out in NIT Raipur. So this is, we can see that the compressive strength is not reducing, or slight increase is there, that we are not taking it as a positive, because our aim is only to check whether the compressive strength or strength of concrete is reducing with this sludge addition. But we didn't see much reduction. That means from 21.7 to 20.8, because 17 MPa is the limit for M20 mixture, but even all the things are above, is around 20, above 20 MPa. Another thing is we need to find whether the sludge is from the sludge, this arsenic is leaching or not. Generally, this procedure is known as TCLP studies. Toxicity characteristics leaching procedure studies. So we carried out the leaching study for both the arsenic sludge and the concrete. And the procedure is like this: 50 gram of sludge or the concrete mixed with 500 ml of solvent, and 1:10 ratio we need to do. And we need to do two tests, that is static leach test and dynamic leach test. So here solvent we are using in static leach test double distilled water, and in the dynamic leach test we are using acetic acid, 0.1 molar acetic acid and 0.04 molar of sodium hydroxide, and we need to mix it and we need to add, that means 500 ml of solvent. In this solvent we add 50 gram of sludge or the this concrete. Then we need to stir it, and duration with different duration, 1 hour, 2 hours, like this 168 hours duration. We need to take the samples at different timing intervals. So this is the trend what we observed in the static leach test. There is not much leaching from the system, but in the dynamic leach test, that means in the corrosive condition, we can say that there is a leaching around 1.2 milligram per liter of arsenic in the water. So that means if you are disposing the sludge in our environment, it may create some issues, environmental issues. So to avoid that, and what we had done is the solidification. Again, we tried, we done the leaching test for this concrete. See, please be in mind that this is very less compared to this one, because the axis you can see it is 0 to 1.6 milligram per liter. It is 0 to 0.008 milligram per liter. Don't think that this concrete is from leaching from the concrete is very high. It is very less compared to this one, compared to the original sludge. So that means some arsenic leaching can be arrested by solidification process. Then coming to, so before starting the other applications or advanced in the aerated electrocoagulation, I slightly coming to another topic, some introduction over electrochemical advanced oxidation process. In the first slide, I already mentioned different process, electrochemical process, separation process and degradation process, in degradation process, oxidation process, and electrochemical advanced oxidation process. So I will slightly explain what is advanced oxidation process, electrochemical advanced oxidation process, commonly in short form we used to call it as EOAPs. So here we are using hydroxide radicals for degrading the pollutants or oxidizing the target compound or any pollutant. So why hydroxide radical is? Hydroxide radical is very highly reactive and non-selective. Because it can be easily generate powerful oxidant. Its oxidation potentially is around 2.85 electron volt. Another issue is even it's harmless, but the issue is its lifetime is very less. It's around 30 nanoseconds in lifetime. That means in short time, it will, at the time of generation itself, it will attack and it will die like that. 30 nanoseconds lifetime only. That is the any other issue with the hydroxyl radicals. So this is the one method by what I mentioned in the earlier slides, that is anodic oxidation. So anodic oxidation, here we are using high oxygen evolution over voltage anodes. That means you may know that oxygen evolution reaction, and I already explained in the initial slides. That means oxygen evolution reaction at the anode and hydrogen evolution reaction at the cathode. It is known as HER and OER. Then if you are coming to the oxidation potential, the electrode potential, oxidation potential of our potential of these electrodes, like platinum, you can 1.3, 0.7, iron oxide, graphite, lead oxide, tin oxide, lead tin combination, Ebenex, it's a commercial name. The silicon doped boron doped diamond, BDD. BDD is known as a boron doped diamond, or titanium doped boron doped diamond, even boron doped diamond. All these electrodes is having higher material is having higher oxidation potential. So that potential we are making use for generating hydroxide radicals. That means if you are using a high oxygen evolution power potential anodes, then this is the M I mentioned, that anode. It will react with the water, that means aqueous solution. Then it will generate hydroxyl radicals in the system. That means only on the surface of that electrodes. This that will hydroxide radical will be produced at the surface, and this can be used for organic pollutants. So that is the mechanism. So here, if you are using the electrodes like iron or aluminum, these reactions will not take place because its potential is very less. Oxygen evolution potential is very less. So hydroxide radical will not generate. Even some journals, it's they used to claim that in electrocoagulation these hydroxide radicals will generate. It's it is having high potential for that means electrocoagulation is not only a separation process, it's a degradation process. No, it will not happen because radical generation will not take place in the electrocoagulation system. Unless in some condition. For example, we tried the iron electrocoagulation and aluminum electrocoagulation for arsenic removal. Then we added sodium chloride for improving its conductivity. Then in the aerated iron electrocoagulation, we saw that this oxidation is taking place. That means AS3 plus is converted into AS5 plus. But thing is, we just check the chloride content before and after treatment. Initially, we added 250 milligram per liter. That is our limit in drinking water. That's why we added only 250 milligram per liter of chloride. Final concentration is also 250 milligram per liter. That means iron and aluminum is unable to degrade, generate active chlorine in the system. So we tried, but some papers they already reported the active chlorine generation in the system in electrocoagulation process. Then we tried a different concentration of chloride. Only we did the electrolysis. Then we checked the initial and final up to 100,000 milligram per liter. We didn't see any changes in the system. But when we applied for a real wastewater, like mixed industrial wastewater or textile industrial wastewater, there the concentration of chloride is very high and it contains a lot of other ions. So you know that wastewater is a highly complex system. Then once we tried with mixed industrial wastewater, that means CETP influent, then their chloride concentration itself is around 9,000 milligram per liter. There we saw some reduction in chloride content, 9,000 to 5,000. So in that complex system, it's very difficult to identify how it is converting to active chlorine. So that is itself, it is a we couldn't find what is the exact reason. But there it is active chlorine. That means chloride is removing from the system, or it may be converted as active chlorine. Then coming to electrofendon process, as I mentioned, it's early in 2000 it started the process. In you know that the Fendon process is started in 1894 something, in that range, by a scientist known as H.J. Fendon. He used that one for small studies like malic acid oxidation by these combinations. But after so many years, in 1960 and 1980, that means after around 100 years over, this reaction comes to a popular. This is the main reaction. That means in acidic condition, if you are adding Fe2 plus and hydrogen peroxide, it will generate hydroxyl radicals. This is known as a Fenton reaction. But in the Fenton reaction, main issue is with the hydrogen peroxide. That means it is costly and it's a highly oxidant, and if its handling is difficult. So when we know that Fenton reactions will take place at acidic pH. So this advantage, these conditions we took as an advantage in electrofenton process. That means if you are using a carbonaceous cathode and if you are aerating in acidic condition, that means acidic condition is required for a Fenton reaction. So the oxygen will, cathodic gradation of oxygen will take place. That means 2 electron cathodic gradation of oxygen will take place at the acidic condition, and it will form hydrogen peroxide at the cathodes, near to the cathode. So that means if you are adding some amount of ferrous sulfate and in this system, hydrogen peroxide will generate by the aeration. So it will react, Fe2 plus will react with H2O2, it will form hydroxide radicals. So that is the advantage of electrofenton process compared to this conventional Fenton process. So this electron-Fenton process itself, another advantage like regeneration of Fe2 plus and pH regulation compared to conventional Fenton process. So regeneration of Fe2 plus, that means in a Fenton process you can see that Fe2 plus is generated with H2O2 and it is generating Fe3 plus, and this is not regenerating. So again, for a Fenton reaction we should have a Fe2 plus for further actions. Then in conventional Fenton process, these two reaction, Fe3 plus it is regenerating Fe2 plus along with peroxyl, hydroperoxyl radicals. Again, it will,
Nidheesh,
yes.
there is one small thing actually. Can you repeat the process? Actually, there is a question from participant actually to repeat the same thing, electrofenton.
Electrofenton, okay.
Yeah, maybe from the regeneration of Fe2 plus.
From the region of Fe2 plus, okay.
Yeah.
Okay. See, this is the conventional Fenton reaction. That means Fe2 plus is reactive with H2O2. It will generate hydroxyl radical in the system along with 1 hydroxyl ions and Fe3 plus. This again it will react with Fe3 plus and OH minus, as in the speciation I have already shown that FeOH2 plus. So that this will convert as FeOH2 plus. But in a general Fenton system, the optimal pH is known as a 3 or below 3, so that Fe3 plus will be always in the Fe3 plus form. As in the speciation, I already shown that it will be in the Fe3 plus form. So the OH minus will be there. So that's why it will this OH minus production, it will shoot up the pH in conventional Fenton process. Okay, and in the conventional Fenton process, you know that hydrogen peroxide is required, and the reactions will take place at the acidic condition. So the handling of hydrogen peroxide is difficult because hydrogen peroxide is having higher oxidation potential around 1.5 or something. So and if you are touching in the skin, you can get the oxidation reaction itself in our skin. Normally we used to use for oxidizing, bleaching purpose and hydrogen peroxide. So that we are using. That means this is another reaction. That means electrolytic reaction. If you are aerating the cathode in the acidic solution, if you are aerating, the dissolved oxygen will convert as hydrogen peroxide by 2 electron reduction. That means in cathode the reduction takes place. As I mentioned, anode earlier, anode oxidation takes place, cathode reduction takes place. So dissolved oxygen reduction takes place, 2 electron reduction. So it will convert as a hydrogen peroxide. So this hydrogen peroxide, it is there. So if you are adding some amount of Fe2 plus, so reactions will take place, Fe2 plus to H2O2. So that is, it will again react with OH radicals. So that is the hydroxyl radicals generation in the electrofenton system. Okay. So, but if you are seeing this one, Fe2 plus, so it is converted into Fe3 plus. So for Fenton reactions, again Fe2 plus is required. So Fe2 plus 3 plus 2 Fe2 plus. That means Fe2 plus should be regenerated from Fe3 plus. Otherwise, it will be converted as a sludge. So for regenerating the Fe2 plus, there are three reactions. This 1 and 2 is a combined reaction. That means this Fe3 plus generated from the Fendon reaction. That means this Fe3 plus is reacted again with hydrogen peroxide that will regenerate as Fe2 plus and it form hydroperoxyl radicals. Again, this Fe2 plus it is not Fe2 plus, it is Fe3 plus. Again, Fe3 plus is reacted with this hydroperoxyl radicals. It form Fe2 plus and oxygen. These two reactions generally occurs in conventional Fendon process, but unfortunately, the rate of this reaction is very less compared to Fendon reaction. That's why in normal conventional Fendon process, we need to add higher amount of ferrous salt and hydrogen peroxide. That normally in the range of gram per liter. So ultimately, what is happening is higher amount of Fe3 plus will be there in the system. So finally, it will generate a lot of sludge. So conventional Fendon process is a combination of oxidation process as well as a separation process. That means coagulation will take place in the system. But in the case of electro-Fendon process, you can see this reaction. That means Fe3 plus generated from the Fendon reaction. It will, because it is a cation, it will attracted towards the cathode. So it will again reduction will take place. So it will convert it as a Fe2 plus. This reaction is a first point in electro-Fendon process compared to the Fendon process. That means this reaction is very fast, so that this Fe2 plus will regenerate it in the electro-Fendon system very fast compared to the conventional system. So this Fendon reactions will take place because H2O2 also generate in the cathode. So ultimately, all the reactions will take place at the near to the cathode surface, because Fe2 plus will attach towards the cathode, hydrogen peroxide will generate at the cathode, Fe2 plus to Fe3 plus conversion will take place at the cathode. Okay, hydrogen peroxide reaction. So it will react at the near to the cathode surface itself. So in the solution, it will the reactions will take place. So most of the reactions is takes place near to the cathode. Then, as I mentioned in the case of Fendon process, we need to add higher amount of ferrous salt and hydrogen peroxide to generate higher amount of hydrogen peroxide, hydroxide radicals. So it will generate a lot of OH minus ion. So pH will shoot up and sludge will generate. But in the case of pH in the electro-Fendon process, this reaction, that means oxygen evolution reaction at the anode surface, it will generate 4 H plus protons. So the OH minus generation will be nullified by these protons. So the pH will be always same. If you are conducting the experiments at pH 3 electro-Fendon process, the final after treatment, it may be around 3.1 or 2.8, depends on the degraded products it's forming. So now again, we are coming back to the aerated electrocoagulation. In aerated electrocoagulation, as I mentioned, it is ferrous ions forming. So if you are adding a persulfate is an oxidant, is ion potential. But the issue with the persulfate is the sulfate radical formation. This is the persulfate. It will not dissociate and form sulfate radicals. So the activation of persulfate is generally required for the generation of sulfate radicals in the system. So the sulfate radicals can be generated from the persulfate or peroxy monosulfate. Two precursors either. We used persulfate for generation of sulfate radicals. It can be done by increasing by adding UV light or ultrasound or heat or heavy metals or activated carbon like materials. So there are so many ways. So this thing we included in our aerated electrocoagulation process. That means in iron anode, Fe2 plus is generating. Okay, then if you are adding persulfate, it will convert it into Fe sulfate radical. This sulfate radicals like these reactions. Again, this will regenerate Fe2 plus by same like H2O2 reaction. Sulfate radicals generate. This sulfate radical also is convert AS3 plus to AS5 plus. So we got a high efficiency compared to the aerated electrocoagulation at different pH because of this sulfate radical generation in the system. And if the pH is alkaline, that means say pH 11 and all, these sulfate radicals, it will react with OH minus ions and it will form hydroxyl radicals also. So in the system, ferrol ions will form, as in the case of aerated electrocoagulation. Sulfate radicals will form by the activation of persulfate by the sulfate radicals, and it will also generate hydroxyl radicals, which depends on the pH. So you will get a combination of oxidants in the system. So the arsenic 3 plus will convert into arsenic 5 plus in rapid manner compared to aerated electrocoagulation system. So if you are considering the oxidation potential, fluorine is the topmost, it's a 3.03 electron volt, but we cannot use fluorine as a oxidant because normally fluorine, if you are adding a fluorine, it is highly reactive and it will form ionic bond with any of the cations. So we cannot use it as a oxidant. So next one is a hydroxy radicals. Then third one is a sulfate radicals. It's 2.6 electron volt, is almost same, and depends on pH and other condition. It may vary from 1.8 to 2.6. Ferrite ions, already mentioned, it's around 2.2. Ferrite is Fe6 plus. Ferrite ions is different. Ours is ferrite ions, Fe4 plus. This is Fe6 plus. Ozone 2.07. Peroxide sulfate ions, that is, I said two precursors for generating sulfate radical. One is persulfate and another one is peroxide disulfate and peroxide monosulfate. This is peroxide disulfate, that is persulfate, both are same. It is having 2.01. Peroxide monosulfate is having very less, slightly less oxidation potential. Hydrogen peroxide 1.78 electron volt. Hydroperoxide radicals, it is 1.7. This is already mentioned in the regeneration reaction. This is hydroperoxide radicals. It is having 1.7 electron volt. So another attempt what we had done is normally in aerated electrocoagulation we used both anode and cathode as iron. But if you are changing the cathode by any carbonaceous material, as in the case of ultra-fun-down process, and if you are aerating, then that means hydrogen peroxide will regenerate, as in the case of ultra-fun-down process. Fe2 plus will generate, as in the case of from the anode. So this will react together and it will form hydroxide radicals. As in the this one, Fenton reaction, this takes place for the pollutant also degraded. Then Fe2 plus will, in the process of because we are adding oxygen, it will convert it as Fe3 plus, and FeOH thrice will, that means sludge will be formed. It will make as a sludge. So then if you are using this thing system for it is generally known as a peroxide coagulation process. That means you can see that it's a modified version of electro-fun-down process. So both electro-fun-down reaction is taking place and electrocoagulation is taking place. So that's why it is known as a combination of electro-fun-down and electrocoagulation, and known as a peroxide coagulation process. So here we are adding oxygen, Fe2 plus, H2O2 is generating, ferrous hydroxide is generating. So ultimately, it will form hydrogen peroxide as an oxidant, and by the hydrogen peroxide, Fe2 plus will react. It will form a hydroxide radicals, Fenton reaction, this reaction. And the ferrous hydroxide is there. That means, as in the case of Shao et al. Publication, it forms ferril ions. All these three, it will convert AS3 plus to 5 plus. So that's why we used to get the rapid removal of this AS3 plus to 5 plus, and ultimately, finally, it will comes along with the sludge, as in the case of aerated electrocoagulation. So this results is already, you can check the results, already published data in Chem Electrochem. And similar to this same reactions, this Berkeley, University of Berkeley group is already published similar data. They conducted an experiment for arsenic 3 plus concentration of 14,464 ppb level, and final concentration less than 4 microgram per liter for ppb level. They used initially only iron electrocoagulation, both iron and iron. There it took 3 hours 20 minutes to reduce this concentration to less than 4 ppb. But in the case of peroxycoagulation process, they are telling that it took less than 1 minute. But it is quite difficult. We will not get that much efficiency in any electrochemical system for this type of reactions. Even if you are general mass balance, if you are checking itself, 1 mole of iron is required to remove 1 mole of arsenic. So if you are from Faraday's law, if you are calculating, it may take, say, around 30 to 1 hour for generating this much of moles of iron for removing arsenic. Unfortunately, they are reported like this. I don't know how it's happened. Then, if you are comparing with peroxycoagulation, that means aerated electrocoagulation, or with electrofendone and anodic oxidation. So we tried with anodic oxidation with platinum coated over titanium as anode and graphite as a cathode, and platinum coated titanium as anode and graphite felt as a cathode, different two combinations. And with and without aeration, we saw that aeration is improving the efficiency, because if you are aerating, it will generate hydrogen peroxide. So that is degrading the arsenic 3 plus. But final arsenic concentration, that means oxidation is slightly taking place, but final arsenic concentration is always same. That means in this process, it can effectively oxidize all the 3 plus 2, 5 plus, but it cannot remove in the anodic oxidation, because after that some separation process is required. Any separation process is required. Same case in the case of electrofendone process. It can oxidize all the arsenic 3 plus 2, 5 plus. You can see the final concentration almost same. At different dosage of iron we tried. But case is it cannot be removed. That means 3 plus to 5 plus is oxidation is taking place. So removal is not taking place in the anodic anodic oxidation and electrofendone process. So, but in the case of peroxycoagulation, oxidation is taking place as well as the removal is taking place. Aerated electrocoagulation is same. We can oxidize it and we can remove it. That is the advantage of this process, two processes compared with other electrochemical advanced oxidation processes.
One small.
Yes.
Can you wind up maybe in another 3 to 5 minutes so that we can have 10 to 15 minutes for discussion?
Okay, fine.
Yeah. Fine.
Okay.
Thank you.
So then the pH is an important for peroxycoagulation process. That means by the hydrogen evolution reaction at the cathode, OH minus will be generated in the system. So the pH will always shoot up. And we need to regulate the pH if you want for if you are targeting the oxidation of the pollutant. So this is the experiment what I had done for my PhD work. This is a peroxycoagulation and a peroxycoagulation PCPH process and PC process, peroxycoagulation process and pH regulator process. The efficiency is also improved and sludge generation will be less. That means the degradation is very high if you are regulating the pH. At different pH, you can see that this is the minerals formed in the sludge and very less other precipitates. That means most of the pollutants are degraded rather than separated. But in the case of pH 6 and 9, you can see a lot of other pollutants. So other applications of electrocoagulations. This is one of the project training from Gujarat University. He came and worked under me, and I given the aerated electrocoagulation topic as aerated electrocoagulation process for mixed industrial wastewater. That means industrial wastewater. You can see that it's a sharp increase in the efficiency, and it is effective in the acidic pH, and pH 7.7 is the normal pH for the wastewater. So up to neutral pH, it is working properly. And if you are adding some amount of hydrogen peroxide, it is you can call it as a modified peroxycoagulation process. So this Fe2 plus will, because this, as I mentioned earlier, this industrial wastewater contains higher amount of pollutant. So this removal is quite difficult. That means a lot of pollutant. So if you are adding some other oxidant, so that this pollutant can be removed. Initially itself, you can remove it. If you are adding some amount of hydrogen peroxide, so Fe2 plus will react with H2O2, and hydroxide radicals will generate, as in the case of Fendon reaction. So that will degrade so much of pollutant. So the load will be reduced. So this is if you are increasing the concentration of Fe3, H2O2, also it is improving higher efficiency. Efficiency is highly improved, both in the case of color and in the case of COD removals. Then this is another applications, that is cyanide removal done by Iranian group Mousavi, published in Desalination. They used iron and aluminum, iron anode and aluminum as cathode for the electrocoagulation of cyanide, but they didn't find this ferrule formation. They didn't go for in-depth studies why it is happening. They just said that it is a electrocoagulation. And this is another study, this done by one of the student, trainee only. She did her MTech in VAT, and then she came to me for doing her MTech thesis. Then we tried with dairy wastewater with different combination of electrodes with air. Obviously, we are getting higher efficiency with Fe if we are using Fe, but the efficiency is very high for aluminum. Aluminum Fe combinations. That means aluminum as a anode and iron as a cathode. And the treatment we proposed was, after treatment, phytoremediation we proposed with general canard species. It is working properly. That means first electrocoagulation, but we got efficiency high for aluminum than iron. Then we tried with aluminum only, not with iron. Then after the electrocoagulation, we tried with the phytoremediation, because the dairy wastewater, only the issue is with TDS. So some amount of TDS is removed and some amount of pollutants is removed. Then we tried with the phytoremediation. It's working. So if anybody is interested, this is an open call. You can submit your articles in this theme area. It is open from up to December 2021 for these topics. If anybody is working, you can call submit an environmental research article. So thank you. Any questions you can ask, and if you want to write, you can. This is email ID. You can contact me through this any of the email IDs. If you want, if you have any attachment, better you send to my Gmail ID.
Yeah. Thank you, Dr. Nidheesh, for your nice presentation. There are a few questions. Maybe I will read out the questions first, and then I will make the forum open for the participants to put their questions directly. The first question is like this, actually. What is the reason for relatively high permissible limits of arsenic, I felt, in India and Bangladesh, even if both are suffering from high arsenic contamination?
That is not in my purview. It is in government purview.
Okay.
That is a policy making. I don't know what basis they made the policy like that. I don't know about why it is happened. But our desirable limit is 10 ppb.
Right. Second question, actually, sir, please enlighten about remedy of seawater to make it fit for drinking or construction work.
Remedy
for seawater to make it fit for drinking or for construction work.
Desalination is best. Desalination plant is there already. Everybody is using industrial purpose, also using desalination is there. Electrodialysis is there. That is also part of one kind of desalination. Or membrane is there. Because see,
Okay.
if you are using for any electrochemical process like electrosorption also, it can be removed, but handling this much amount of chloride and sodium removing from electrosorption or electrocoagulation is difficult.
Okay. Right. So other question from, I hope some of the participants. What about using carbon electrodes?
Carbon electrodes where? In electrocoagulation?
Maybe for Adulya, can you put forward your question? Actually, it's her question. What about using carbon electrode? It is for electrofendon or it is for electrocoagulation?
Coagulation, sir.
Yeah,
She
for
has
electrocoagulation.
See, electrocoagulation, see, if you are using a carbon, I think her question may be using carbon for as an anode or cathode. Adulya, please. You want to use it as a anode or cathode? As an anode material.
Anode. Yeah.
See, if you are using a carbon as an anode material, see, some amount of carbon will comes into the solution. It depends on the electricity if you are using. But it will not go for an electrocoagulation because see, electrocoagulation occurs only if it produces some amount of hydroxides. See, these hydroxides can be produced only by metals. Carbon is commonly known as a stable electrodes. Graphite, all these things. It's the carbonaceous material, all are stables. It is not a sacrificial anodes. Only sacrificial anodes, that means metal electrodes are useful for electrocoagulation process. I think I cleared your doubt.
Yeah, hopefully. Yes. Few more questions. Just wait. There's no questions from here. Right. What's the shelf life of electrodes used in electrocoagulation process?
What is the
Shelf life of electrodes used in electrocoagulation process? Maybe you can explain for electrofendon also, sir.
Shelf life of electrode? See, if you are, I can't say it's infinite. That means if you are optimizing the system with a low voltage, that means if we can optimize the same efficiency with if you are the space between anode and cathode is very less, then the optimal voltage will be very less. So like that, then the amount of iron coming out, amount of iron dissolving from the anode will be less. But at the same time, we will get a higher efficiency. So normally we can say that theoretically we can say that it is we can say it is infinite. That means up to that life of the anode for an electrocoagulation process. But in the case of electrofendon, the anode, normally we will use BDD and all. Its lifetime is, they used to say it is 5 years or 10 years lifetime. If you are using an BDD, but it's a costly electrodes, boron of diamond and platinum and all. It's a very costly. Their lifetime, they used to say it's 5 years. And the problem is in electrofendon is associated with the cathode, because we are using carbonaceous cathode. All the cations will be deposited over the surface. 1 minute. Hello. I will call you after some time. I am in meeting. Okay. So that is the issue with electrofendon. Only the issue with cathode, and that is a working electrode for electrofendon also. But it's very difficult to control the reactions that the electrode deposition all. So in both cases, the passivation is the issue.
Abhinaya or Lakshmi, can you read up the questions? Actually, there is a network issue, so I couldn't see the questions.
okay, sir. Sir, there is another question.
There is a question.
Abhinaya, shall I continue?
You can continue.
So there is another question. Is it really possible to remove highly carcinogenic heavy metals such as mercury and arsenic present in different water bodies? It's from Dr. Manoj Singh.
We can remove it. Electrocoagulation is able to remove all the contaminants.
Okay. Shall I read the other?
Please go ahead.
In conventional coagulation process, is it feasible to recover alum from primary sludge? It's from Akansha.
See, yes, I don't know how, it's quite difficult. Recovering alum, what is the need of alum? Because alum is not present in the sludge. Because if you are adding alum, it will convert it as aluminum hydroxide. So that is coming as a sludge. Sulfate may be there in the water. So how I can recover alum from the sludge? It cannot.
Okay, sir, there is another request. Can you post a special issue detail again?
Okay. This is related to advanced electrochemical treatment for water and wastewater decontamination.
1 minute.
It is,
1 minute.
yeah.
I hope you are not the presenter now. 1 minute. I will just make you present. 1 second. 1 second. Yeah. Fine.
Is it visible? Is it visible now?
No, sir.
Wait, I will share one more time again.
1 second. Actually, there is issue from my side. Maybe what we will do, actually, poll will be continued later on. Okay. Just I am halting it. Poll will be continued later on.
Okay, I will explain that one. 1 minute. Hello. I am in meeting. I will call you after some time. Okay. This special issue is in environmental research that is already available in the environmental research, the Elsevier journal itself. In the website, you can, if you are going environmental research website, there you can see at the bottom call for papers. There you can see the details about the special issue. There are so many special issues. My special issue is on advanced electrochemical treatments for water and wastewater decontamination. So it is theme area includes chemical advanced electrochemical advanced oxidation process, capillary deionization, novel electrodes in electrochemical treatment, electrochemical hydrogen production, scale up of electrochemical cell, passivation reduction in electrochemical cell, electrochemistry and nanotechnology, integration of electrochemical technologies and advanced oxidation process. So these are the theme areas. So that is available in the journal website itself.
Okay, sir. Thank you. Sir, there are many messages congratulating for the nice presentation by the participants.
Okay, thank you. Thank you for all.
Another thing, sir, shall we conclude now?
Yeah. So, Dr. Nidheesh, actually, so it is for just an information. Actually, we two work together from MTech in NIT Trichy. That is from 2009 to 2014. We were together at NIT Tiruchirappalli. Then we were into different locations, and finally he's in NEERI, and I'm in NIT Calicut. I hope like many of our works are going together, and hope it will continue. And on behalf of Department of Civil Engineering and FTP coordinators, I really thank Dr. Nidheesh for the wonderful section, giving in-depth knowledge on electrocoagulation, electrofendon, aerated electrocoagulation process and its allied research areas, and also like comparing the different research groups outputs and whether it is how far it is reliable, how far it has to be reproduced. So all such things. And thank you, Nidheesh, for your wonderful section. Thank you very much.
Thank you, Anand Singh, for inviting me.
Yeah. So
okay.
Thank you.
I think there is one question: is review paper accepted in the special? All research and review papers are is available. No problem.
Yeah. Okay. So thank you all. So the poll is again opened. So you can continue the poll. So thank you, Nidheesh. If you want, you can leave now. Or,
Okay, I will leave now.
yeah.
Thank you.
Yeah. Thank you. Thank you very much. Participants, yeah. Go ahead with the
So
poll.
shall I continue?
Yeah. Sure.
Dear participants, we will continue after a short break of 15 minutes. You can continue with the poll.
So kindly
Thank you.
join at the time. See, the session will start exactly at 11:30. Be on time. Okay, Lakshmi, just I'm making you as the host.
Yes, sir. Okay.
Yeah.